Hello, welcome to ELEE2250 Lab 1 RC and RL circuit. As you can see in the lab manual, figure 1.1, the construction of the RC and RL circuit can be very straightforward because there are only two components. For RC, there's only one resistor and one capacitor. For RL circuit, there's only one resistor and one inductor. Please make sure that you have played with the breadboard before you construct the circuits, so you understand how it works, on which line you want to connect to. So if you have any difficulties, please raise your hand during the lab session and let me know. Let me check your circuit before you even connect with the power. By look at the RC circuit, if you connect with a resistor and a capacitor, and the output is over the capacitor, this is considered as a low-pass filter, as shown in figure 1.1a. It attenuates the low frequency and reject the high frequencies. Also, the high-pass filter will operate the opposite. They reject the low frequency and passes the high frequencies. This is the breadboard we want to work on. So let's have a look at it, how to get this going here. So I want you to have a look. On the right hand side, the circuit here is a particular low pass filter. So in the breadboard on the left, this is R, component R, this is the capacitor right there, C. So basically this is resistor, connect with the capacitor, and then you put a AC power supply right here. This will form the circuit. So make sure this is all connect all together. So in the function generator, you can have a clip, an alligator clip here. So you know all the breadboard work this way. All the dot in here all connect together. All the dot here also connect together. And this side, this dot here connect together. And this, all 5 holes are connect together. So, and then in between there's a gap. So they are not connecting together because that's why we put a resistor here. So these two are not connecting together. If you put these two in here, that means you're shorting the resistance. And also you can see on the left hand side or right hand side, two vertical lines here. They're all connecting together, pretty much. And there are more than one way to build this RC circuit. So, but this is my preferred way because it builds from left to right. Let's erase these ones. Say you can build a circuit in different ways. So because they are all connecting all together here, so you can put you can use the little gap here. This is also a gap, but it's not as big as this one. You can put a resistor here. And also because it's all connecting together, you can put a capacitor here. And then you can put the input right across here. And this will be your output, the output. Or you can use in the gap, you can use in this one, the resistor here. And then put another capacitor here. So this will be your V in. This will be your V out, and this will be your V out here. But I still prefer this way because it's the simplest way you can build and also easy for you to debug later on. So let's erase this too. If you're still confused about how to using the breadboard and how these holes are all connecting together and like this, that, please let me know. We can talk before the lab or after lab. Okay, let's go back to our slides. Here. So this is the oscilloscope we use in the basement, the B035 TDS2002. So you can see the channel 1 here. You can see, follow the cursor. Is a yellow button. No, not yellow button. Yellow button right here. You can see this first line is yellow right there by default, and channel 2 is blue. So this, when you're turning on, this something will be looking like this. It connects nothing. And those on the left, on the right hand side here, are the soft keys. And this button right here to call auto scales. You can press on it once you connect the circuit. And next one we were showing you is the input and output comparisons. This is the waveform from this circuit, the one we just built. Let's look at this circuit again. So let's take a picture here. So the yellow one is the input, and that we're not very interested because we set it up. The set input is 6.6 volt peak to peak. This is peak to peak. And the input channel, the frequency is 524 Hertz, and the yellow one is the output. So you can see because you can assume here is a soft key here. You can select, you can get the channel 2 peak value. You can by pressing many times to make your selections, and you can get even the rise time. We cover rise time momentarily. So this basically you can reach. You can see this peak value of the output is 200 millivolts. The question is why 6 volts and 200 millivolts looks not much difference? Because of the division, the voltage division. We didn't change because we have auto scale selected in. So in this way, oscilloscope will make this comparison that we can make this we can say you can compare this two waveform. Otherwise, if you have the same voltage division, so this output will be looking very, very tiny. Okay, so let's go back to our slide. Okay, let's go back here. So next topic we're going to cover is about the cutoff frequency, which is a very key feature of the low pass filter or high pass filter. By definition, is the ratio of output input that has a magnitude of 0.707 or 1 over square root 2, and this is considered as minus 3 dB, and also considered as cutoff frequency. This is by definition. The cutoff frequency can calculate this way. So you can see C here stands for cutoff, F of course is frequency, is equal to 1 over 2 pi times time constant tau. So tau for the RC circuit is R times C, and for the LR circuit is L over R. This is by definition for the cutoff frequency. You can get a time constant. So next graph showing you without knowing the R and C value or L and R value, by looking at just the output graph, you can find out what the constant is, what the cutoff frequency is. So basically, if we go back to this waveform here, so let's erase this one. So this again, this one is the output value. Output frequency. I'm sorry, output waveform. So if we want to say this one is 200, this one is 200 millivolt. So it's about 63% here. This will be your time constant. So time constant tau. We got a time constant, so we can get a frequency equal to 1 over 2 pi tau. So without knowing the R and C value, but just look at the graph, roughly about 63.2%, we can get this time constant. There's also a button called cursor on the oscilloscope. You can measure these two cursors. You can select time scale, then you can have two cursors, and then automatically on the right hand side you have a delta value about this interval. Go back here. This is pretty much an ideal graph here, showing this around 63% of the output graph. So this will be your time constant tau. So next graph, let's interact with this one as well. Actually, let's go back here. Let's interact with this one. This is very straightforward. So this is input. So this square wave, this basically can consider as this square wave coming in, and I have an input and output, R and C. So this on the rising edge. So this is about 10% of the final value. This is about 90% of the final value. So the time from 10% to reach to 90%, this considers T rise time. On the other hand, on the falling edge, from 90%, it's the same line, 90% up to 10%, up to the falling edge, this is T fall time. So basically, if you have a switch here, so when you switch it on, so you start charging the capacitor. So this basically is the charging part, and this is the discharge part. So if you open the switch, you can see the capacitor discharging. This is the discharging part. Okay. Let's go back to the switch here. Basically, this talk about the definition of rise time and the fall time, from 10% to 90% on the rising edge, and fall time is 90% to 10% of the falling time. Also, the settling time we can consider is from here. So this one is from here. This will look like a lot of vibrations here. So this is going to be around 2%. So how much you reach the final value becomes finalized. So this is how much time it will take. But this is not a settling time. This is not under the scope of this lab, so we don't really measure the settling time here. So it just gives you some definition here. So go back there, back and forth. So a delay model, so you can use in the RC circuit, has used a delay model. Basically, let's see this propagation delay time. I forgot to mention this. This is the propagation from high to low, low to high, and propagation delay from high to low. So from a rising edge, from falling edge. So this again, this is not we're not really investigate these two values and settling time, but it's showing you the definition of this graph here. So a propagation delay circuits, actually for RC circuit, can be using for computing systems. Actually, they can build assume there's a square wave coming in, and they go through the RC load. The longer the delay, the slower the computer is. And on the other hand, the faster the circuit is, and then the shorter the delay is, and the faster the computer is. And that's why we got some supercomputer they built a few years ago. They were super fast. A wire also can be modeled as a cascade section for simple RC and circuits, as shown within the next two slides. Assume there's one square wave coming in up to one end, and then it will take some time to reach to the another end. So the delay time can be calculated based on the value of the R and C. So the longer the wire and the more section you can put it in, something like this. Let me interact with this one. Say we have a two-stage of RC circuit, so we can consider this is stage one. First stage. This is what we consider the second stage. You want to build more, you can build more. Here we consider the third stage. We consider fourth stage. So in this how will be output. Okay, and at the very end, I want to touch base for the half power definition for the 3dBs. Basically, this is the equation right here. Say if the voltage has dropped to 1 over square root 2 of the maximum power, you can get the 3 minus dB. The calculation here is 10 times the log over 10 over 1 over half. So half of the power of the input, and then you can this become minus 3 dB. So it's some questions or some quizzes or some online exercise can use this equation to ask you how to calculate the current or voltage, because that's how we define 3 dB from here. At the very end of the video, I want to mention there's going to be a quiz, multiple choice for you to exercise, and hope you are going to have a lot of fun. Good luck to your quiz and the lab. Thank you.